Okay, so moving on, talking about quantum mechanical stuff, and let me talk about the wave-like properties of electrons. So electrons do also have wave-like properties, and we can calculate them based off of their wave-like properties. So let's do this. Calculate the wavelength of electron traveling with speed of 2.65 times 10 to the 6 meters per second. So to do this, we have to use the de Broglie wavelength, and the equation is wavelength is Planck's constant over the momentum, which is h over mass times velocity. So let's apply it for this here. So it's the d, I should say, lambda d. So lambda d, so the de Broglie wavelength is going to be h 6.626 times 10 minus 34 joules times second, all over mass of the electron. The mass of an electron is 9.11 times 10 to the minus 31 kilograms. 31 kilograms. And the velocity is 2.65 times 10 to the 6 meters per second. Okay, so let's look at the dimensionality. Right, we have joules times seconds over kilogram meters per second. So, which is joules seconds squared over a kilogram times meters, and a joule is a mass times a Newton meter. It's a mass times acceleration is a Newton. Acceleration is meter per second squared, Newton meter squared. So that's a joule, seconds squared all over a kilogram meter. So looking at the units, kilograms cancel, seconds cancels, and one of the meters cancels. So we're left with a meter. Okay, so then put this in our handy dandy calculators, and we get 2.74 times 10 to the minus 10 meters. So that's roughly more or less half the size of a hydrogen atom. So that's a very, very small wavelength. And that's an electron. So really, really small wavelength. And then look at that. Okay, so what happens? What about us? What if instead of an electron, you put your good old instructor? I'm about 118 kilograms. So what's going to happen if you put me in there instead of that? The difference is on the order of 10 to the 33 difference. So that means if I was traveling this fast, my de Broglie wavelength would be some number times 10 to the minus 43 meters. So my de Broglie wavelength, even at speed, is going to be so small that it's not really. I mean, a macroscopic thing like your instructor is not going to be usable really for this. So the Broglie wavelength only works for really small things. Okay, so recap on this one. I don't know. I really need a recap. It's pretty simple. Just apply the Broglie wavelength. Apply the equation, and we doing the units. You get 2.74 times 10 minus 10 meters. Okay. So let's see if you can do this backwards. So what is the velocity of electron with the de Broglie wavelength being that? Let's see if you can do it the other way. So lambda d is h over mv, which means v is h over m lambda d, d 6.626 times 10 minus 34. Actually, I forgot to calculate this one out beforehand. I can do that really fast. 6.626, 34. Okay, if you throw in your calculator, you get that. Okay, moving on, we're going to talk about the uncertainty principle. And this is Heisenberg's uncertainty principle. And I mentioned Schrodinger is someone I would love to meet. Heisenberg is someone I would love to punch in the face. Um, he, uh, well, that's a different story. He was very, very militant, to say the least. Okay, but he did do some good stuff for science. Here's Heisenberg's uncertainty principle, and is the uncertainty in the position times the uncertainty of the momentum is greater than or equal to h over 4 pi. Sometimes you might see something called h bar. H bar, this is h over 2 pi. So if you see h bar, that's what that is. And the idea is that there's only so much we can know for certain. So the ends, and because of that, electrons and other particles have uncertainty in their position and where they're going. So so this is something we can't exactly know where something is or where it's going at any given time. And this is a big deal for people back in the day because many people believed, and some people still believe, in fate. So the idea was, oh, so we can figure out where the universe is headed and where everything's at. We know exactly how everything's going to turn out. We can figure out how the stock prices are going to change. We're going to figure out who you're going to marry, and all is going to be fine. This has all been destroyed with the uncertainty principle because there's uncertainty in where you're going, and things can change. So to give you an example of this, here is the classical trajectory. This is like if you have a tank shooting a round and it's going that way. What if you have tanks firing quantum mechanical rounds? Well, there's uncertainty of where it's at and it's going, and you don't really know where it is or where it's going at any given time. Another way of looking at this, though, is the strike zone, that there tends to be a certain density of particles in a certain area at any given time. But we know kind of for certain or kind of a general idea where things at. This is the way an electron is. Unlike a baseball where it's in one spot, and an electron is actually in all these places at the same time. So it's not that it's you can't find it. It's just all these places at the same time. Let's go back to someone cool like Schrodinger. And Schrodinger used some of these to develop his famous wave equation. And his wave equation is h psi. That's a psi that looks that funny thing that looks like a fork, like a pitchfork. That's h psi equals e psi. Okay, so h psi is known as the Hamiltonian operator on the wave function, and then the energy levels of the wave function comes out. So this is, if you go and study linear algebra, this is typically taught beyond calculus, the energy levels are known as the eigenfunctions of a matrix. So you have this array of numbers, and then you can write out what are known as the eigenvalues. The Hamiltonian will operate on the wave function such that the energy levels of the electrons come out. And an operator, so I've put some operators there. There's a plus, minus, multiplication, division. Those are operators. When you have 1 plus 1, you are telling that plus sign is telling you to operate on the other numbers such that you add them together. That is an operator. So the Hamiltonian is an operator that operates a specific way on the wave function. So you have to figure out what the wave function is. And also the Hamiltonian operator is just the kinetic and potential energies of the electrons. So that's if you're wondering what it is. The Hamiltonian is pretty easy. The wave function is what's hard. So discovering the wave function. And also, if we take the integral from negative infinity to infinity of the wave function with the vector dot product of its complex conjugate, and then integrate that over all space, so d tau is all space. So if we do that integral, we get what are known as the probability functions, which we'll show you some of these later on. So that's where the shapes of the orbitals come from. Is that from that right there? And the complex conjugate, that's like if you have something that's like 3 plus 4i, the complex conjugate is 3 minus 4i. That's what the complex conjugate is. So when I was studying this stuff, what amazed me among other things is that all that math. So when you study math, you're like, oh, I'm never going to use this stuff ever again in my life. It turns out that all those crazy things like Green's theorem, that's just a weird doing integral loops over things. I remember studying, I'm like, yep, never going to use this again in my life. Nope. Guess what? I've used Green theorem before, and I've used it for a practical application in quantum mechanics. So all that crazy math actually has a purpose. So remember that, students, study your math. Okay, so it's a little simple for the hydrogen atom, so we've solved it for the hydrogen atom or hydrogen-like atoms. Hydrogen-like atoms means 1 electron. And the energy levels are that it's minus 2.18 times 10 to the minus 18 joules times 1 over n squared. So we'll get to the n. N is the principal quantum number, which we'll get to soon. And the idea here is that if we have a free electron has 0 potential energy. So we just pick this as the free electron has 0 potential energy, and a bound electron has negative potential energy. So we've picked the relativeness of our scale to be a free electron. So that's all. This is human derived, and this is actually the easiest. So we pick our 0 to be a free electron. Otherwise, let's say we picked a specific energy level and atom to be the relative, then we would have to calculate another electron relative to that other number, and then we'd have to do 2 or more calculations. This way, you only have to do 1. So that's nice. It was a good choice. So, okay, but we'll come to this stuff later. But let me build up the idea of quantum numbers. And this is how they work. So I mentioned before, n is the principal quantum number. Oh, also I should mention, this is going to sound really weird. Listen to this, watch it, think about it for a day, come back, maybe watch it again. Maybe it'll make more sense, but eventually it will make sense. But it's kind of weird. I think it's cool, but hey, that's me. Of course, hopefully I think it's cool. I'm the teacher. All right, so principal quantum number, n, and n exists as whole numbers, positive whole numbers. So n can exist as 1, 2, 3, 4, 5, on up to infinity, and whole numbers. And then we're going to talk about the next quantum number. We call it L, the angular momentum quantum number. L exists at, L can be 0. It can be 0, 1, 2, 3, all up to n minus 1. Okay? And if L is 0, if we say something has an L of 0, we call that an s orbital. If L is 1, we call it a p. L is 2 is d. L is 3 is f. And people wonder what those letters mean. S means sharp, P means principal, D means diffuse, and F means fine. And those are spectroscopy terms. It does not mean spherical perpendicular for S and P. That is not where that name came from, although it is what the shapes of the orbitals are. But those are old spectroscopy terms. Okay, moving on. We have the m sub L, which is the magnetic quantum number. The magnetic quantum number exists minus L plus 1, on through 0, then 1 to integer steps up into L. So that is the bounds of m sub L. And then this is not included in the next chapter, but I like to talk about it now. The spin is either plus 1/2 or minus 1/2 for electrons. And again, this is next chapter, but I like to talk about it now. The Pauli exclusion principle. No two fermions may have the same set of quantum numbers in the same atom. So this is a Pauli exclusion principle. And electrons are fermions. So what is a fermion? Fermion is something that follows Fermi-Dirac statistics, and it means that their spin is a ratio of integers that are not that's not an integer itself. So I mean, I know 1, for instance, can be a ratio of 2 divided by 2, right? But 1 is also a whole integer by itself, a whole number by itself. But 1/2 is a ratio of 2 integers that's not a whole number itself, right? So electron spin is a half. So what is a spin is the next question. Electrons have this fuzzy cloud of stuff, and it's in many different places at once. It has electronic magnetic field associated with it, but at any given time, the magnetic field is focused in a certain direction. This direction can change, usually changes. It may not change if it's cold enough, for instance, and it's in a certain environment, but it usually changes. That direction of the projection of all the magnetic field of that electron at a given time, that is the spin. And so electrons have spins that are fractions, therefore they are fermions, and therefore the Pauli exclusion principle exists for it. Bosons, though, follow Bose-Einstein statistics. They do not, they have a Bose-Einstein condensate. They do not follow the Pauli exclusion principle. Bosons have integer spins. So a photon is a boson. And what's interesting about bosons can have the same set of quantum numbers. And if you have bosons that have the same set of quantum numbers in the same environment, that's known as a Bose-Einstein condensate. So you can get matter occupying the same space at the same time. You can stack as many as you want on top of each other. So this was done with, I believe it was ruthenium atoms in Colorado, many years past. So we've done this, and photons do this all the time. Photons they can stack up on top of each other. It doesn't bother them at all. Electrons, on the other hand, they do not. And the Pauli exclusion principle, this explains why matter has structure. So because of this, the atoms build up, and they have structure to them. And we'll talk about this a little bit more in the next chapter. But I like talking about this now because that's when I introduce the quantum numbers. Okay, so let's look at this. What are the quantum numbers and names of the orbitals in the n equals 4 principal quantum numbers? How many n equals 4 orbitals exist? So n equals 4, that means L can be 0, 1, 2, 3, and 4. Then m sub L, this has to be 0. For 1, it's minus 1, 0, 1. For 2, it's minus 2, minus 1, 0, 1, 2. For 3, it's minus 3. Oh, wait. L cannot be 4. Sorry, it's minus 3, minus 2, minus 1, 0, 1, 2, 3. And what are the names of these orbitals? This is the 4s orbital. These are the 4 p orbitals. These are the 4 d orbitals. And these are the 4 f orbitals. How many orbitals exist? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, which is also equal to n squared. So 4 squared is 16. 16 orbitals or 32 electrons can populate those orbitals. So, okay. Now quantum number two. One set is erroneous. Which one is it and why? So if n equals 3, L can be 0, 1, or 2. 0 is fine. If L is 0, m sub L has to be 0. That's fine. Okay, B. If n is 2, L can be 1 or 2. L being 1 is fine. If L is 1, m sub L can be minus 1, 0, or 1. Minus 1 is fine. That's okay. For C, n equals 1. L has to be 0. If L is 0, m sub L has to be 0. That's fine. For D, n equals 4. That means L can be 0, 1, 2, or 3. L being 1 is fine. If L being 1, m sub L has to be minus 1, 0, 1. M sub L being minus 2. This is wrong. This is the one that's erroneous. It's why m sub L can only be minus 1, 0, or 1 based off of that. Or L can be 2. That would be fine as well. So let's see if you can figure out which set of quantum numbers is erroneous. So think about this. And same logic, it's that one. Okay, so I like using this example for excitation. Let's say we're good friends, and I invite you over my house to watch a Super Bowl party. So I have a Super Bowl party, and I have my TV, and in front of my TV, I've got this really sweet lazy boy. Right, so here is this sweet couch, lazy boy, right in front of my TV, and behind that I have this comfy couch. And then back on the couch, I have these hardwood chairs. So if you are the first one to the party, where do you sit? You will sit in, well, you can't really see that. What color? Pink. You're going to sit right there in front of the TV. And then let's say, and if you're the next person, well, first thing you sit in front of the TV, then the next people, they come and sit on the couch. And then some unlucky soul gets the chair. So what's going to happen if person in the lazy boy gets up to go to the bathroom? What's going to happen? Well, there's going to be a mad rush for someone to go into that chair, sit in front of the TV, right? Because it's a better seat, it's close to the TV, and what do you do when you sit in the TV? You relax, like, I am relaxing now. And you have that relaxation. Okay, so, and my analogy, of course, is that electrons behave the same way. So, electrons like to be in lower energy states. So, like, let's say, you know what, I want you to do the next thing for 10 hours. You have to pick one activity to do for 10 hours. What is it going to be? It's going to be something low energy, right? I'm going to be sleeping. I'm going to be on the couch watching Netflix, right? You're going to pick something that's really, really low energy. No one's going to say, you know what, I'm going to sprint for 10 hours straight. Like, well, we couldn't. We would die, of course. But, you know, we're not like, I'm going to be climbing stairs for 10 hours. So that's That's, that would be we could do that, but that would be pretty sore the next day to say the least, right? So we pick things that are low energy. So electrons, if they are in an excited state, a high energy state, they will drop down to a lower energy state. And as they drop down low, they will relax, relax down. So, okay, so instead of TV, let's say we have an atom's nucleus and we have energy levels. And electrons are going to populate to the lower energies. What happens if it's excited? We have excitation, it goes high. And then when this electron goes down in energy, it relaxes, has a relaxation, and it gives off a photon of light. If it's a lower jump, say it's here, and it goes down, it's going to give off a photon of lower energy. And the lower energy photon I'm drawing, it's red, and the high energy photon I'm drawing is violet, if you can't see the colors. So, and this is what's happening to atoms. So excitation, relaxation. So if you have, in the n equals 1 level, energy absorbs electron. If it's unstable and it wants to relax down, when it relaxes down, it emits light. And this is the spectrum for hydrogen atom. The hydrogen atom here. And you have the going down to the n equals 1 level. That is also known as a Lyman series. And the visible wavelength, this is known as the Balmer series. And if you ever look at a hydrogen lamp, it has a pink kind of fuchsia color to it. And it's actually all these colors together. Our eyes just blend together. Our eyes, we covered this last talk. Our eyes are not spectrometers. We know we're bags of chemicals that seek out food and run away from predators. So we have to think fast. We don't think, oh, gee, what's the quantum mechanical level of that? We're not spectrometers. We don't discern things. We just get a big signal jumbled to our brain, and then we interpret it. So, okay, and the energy level for these change. It's the same thing as this level here, the hydrogen atom level. Where is it? It's right there. Energy En for the hydrogen level. It's just final minus initial. Final minus initial. And using that pre-number there, it's called the Rydberg constant, that R infinity. And remember, a free electron has 0 potential energy. A bound electron has negative potential energy. This is a way of bookkeeping. Okay. So let's do this. Determine the wavelength of light emitted when the n equals 6 level to the n equals 5. So let's do this. And the change in energy is the Rydberg constant, 2.18 times 10 to the minus 18 joules. Okay, so the delta E, let me use blue. This is the Rydberg constant, and final 1 over 5 squared minus 1 over 6 squared, which is Rydberg 1 over 25 minus 1 over 36. Okay, so that is the energy of the photon that comes off. So this is the energy of the photon. And if you remember, energy of the photon is h nu is hc over lambda, which means that wavelength is hc over E, which means our wavelength is h 6.626 times 10 to the minus 34 joules times seconds, 3 times 10 to the 8 meters per second, all over the energy, 2.18 times 10 to the minus 18, 1 over 25 minus 1 over 36. So, and of course, this is I'm taking this and putting it right there. So, okay, then you put this into your calculator and you get 7.46 times 10 to the minus 6 meters, or also known as 7460 nanometers, like so. Okay, so should do a recap on this one. What we want to figure out the wavelength of light. So if we have, I'll put it up here, the n equals 6 level. So we have an electron here that's going down to the n equals 5 level. What is this? What is this wavelength of light coming off from that? So we first start off by calculating what that energy change is for the electron. The energy change for the electron, it's from going to 6 to 5, it's going to lose this much energy. Okay, and it's losing that much energy, and then applying this equation here, we solve for the wavelength, and we put the energy in there, and plug in Hc over that photon energy, and we get 7,460 nanometers. Let's see if we can figure this out. What is the energy of the photon emitted as it goes from the n equals 3 to n equals 1 level? And this is going to be 1 over 9 minus 1 over 1, or 9 ninths minus 1 ninth is 8 ninths. Right here. Okay, so the next question is, why did I put a minus sign here, and why did I not include a minus sign here? So that's the delta E for the photon. So I told you one of the things I think about is I always think about where the energy is going. So the energy of the photon is going to be a positive number. The energy loss, how much energy the electron is losing, is a negative number. So that's the equation kind of depends on what you're looking at. I mean, the magnitude of the equation is the same, but the interpretation of it, where the energy is going, what it means, that is where the negative signs come into play. So that's just the way I think of things, for me personally. Okay, we mentioned this, the orbital shapes. We have the integral of negative infinity to infinity of the wave function time vector data with its complex conjugate over all space. And if we do that, we do start with the 1s orbital, we get a sphere. And you get a probability density where you get a lot of, you have, I'll go back to orange, you have quite a bit of probability in the nucleus, and then it's decreasing as you go out. So, and that's the probability density. Then you look at the radial distribution function, so that's just the density. Then you look at, you slice an atom up by looking at spheres as it's going through, and you get this here, the radial distribution function for it, where the y-axis here is the total probability, x-axis is the distance from the nucleus. And notice something, that you have a rise right here, which means, and looking at this graph, the interpretation is, you know what, the electron actually spends time in the nucleus. And the answer is yes, it does. Electrons can and do have density in the nucleus, especially the 1s orbital. So what you learned in high school, if you took that, like, electrons are not found in the nucleus, that's wrong. Electrons are found in the nucleus of the atom, but not very much. So the effect of that is not that much. There's a particle called a muon. Muon has the same charge of an electron, but it's much more massive. The muon has much more density in the nucleus, so some people like to study muonic atoms because of this fact. Like, oh, this is kind of cool. So I've never studied muonic atoms, but I know that that's one of the things they look at. The other orbitals beyond the 1s, they have increasingly less density in the nucleus. So let me talk about nodes. So imagine I see people doing this in the gym sometimes. They have these big ropes and they start shaking the ropes back and forth. Let's say that you shake that rope really, really hard, and you can. So here's like a person holding a rope, and you attach to the wall. If you shake it really hard, you can get like a kind of a loopy jump rope thing. If you keep on shaking your arms harder and harder, eventually you can form something where you have these two lobes. Those are known as nodes. And these are also, this is a quantum mechanical function where you have a boundary condition. There's also these like wind instruments that you can buy. They have these tubes. You roll them around and it goes whoa, 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 whoa. And if you keep on spinning it faster, it goes whoa, 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 whoa. It changes the pitch. And that has to do with the same idea with the nodes. You have a fixed boundary condition, and then if you swirl thing up, you put enough force to it, you will get quantum levels. I guess my voice is a little deep. I really can't, so it would be like whoa, 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 whoa. I'm careful with my voice there. It's just the pitches can change, and as you go to higher frequency or whatever, there's more nodes, and the nodes are areas of zero density, and we see these in electrons. So the 1s orbital has no node, but if you look at here, the 2s orbital has a node, and the 3s has two nodes. So the number of nodes that you have is the n, is the principal quantum number. The number of nodes is n minus 1, the principal quantum number minus 1. And these are areas of zero electron density. You see no electron density there. And this is also what's strange. You're like, okay, here's the electron. It has density here, a donut here, and a big donut here. Where's the electron? It's actually in all these places at the same time. So it's not like it dances around and just reappears. No, it is in all those places at the same time. Now here are the p orbitals. P orbitals here, I told you they're not mean perpendicular. The two p orbitals, they have a node at the origin. So the p orbitals do not have very much electron density in the nucleus of the atom. Another thing about the p orbitals, they have signs to the wave function. We don't really talk about this that much in this course, although we talk about it a little bit in bonding. So the wave functions have signs, and this would be the positive sign, that would be the negative sign for it. And this is important when it comes to bonding, how the orbitals overlap, and the new orbitals that form. So there's the p orbitals, and then here are the d orbitals. So these are kind of cool. These are the 3d orbitals. And notice a couple things. So the dyx, dxy, and the dxz, they're all kind of like four-leaf clovers. Then you have the dx squared minus y squared. These are along axes, and these orbitals, these can then easily bond with two atoms. Same thing with the dz squared orbital. And these orbitals are real, and they have real effects. When metals bond, especially transition metals, they usually bond with these two, at least when they bond with each other. You can get a phenomenon called back bonding with this type of orbital, which I'll talk about a little bit later. So if you remember the back bonding, that's how cyanide and carbon monoxide can kill you. They bond via back bonding. But these here, this is where transition metals will bond. And there's also something called the Jahn-Teller effect dealing with a DZ orbital, typically for copper complexes. So the copper complexes will elongate alongside the DZ orbital, and they will change their geometries. And that's something known as the Jahn-Teller effect, and that specifically has to do with this shape of the DZ squared orbital. So it's not like I'm making this stuff up and it has no application whatsoever. It does have an application. There are some real consequences of these orbitals being the shapes that they are. And here's the f orbitals. They're just really funky. These are the 4 f orbitals. These I think it's cool. I always thought it was kind of fun. Oh, and I mentioned the phase of orbitals. So mentioned here, it's more important we get to bonding. And then we get, why are atoms spherical? Atoms are more or less spherical. So if you think, okay, here is the s orbital, it's spherical. Here are the p orbitals. Here's one here, and then there's one that goes there. Then we have the d's. You have this d. You're going to have this d, and then that plane there. Then you have the x squared y squared there, and then you have the dz squared with a donut. And if you look at all that, that's kind of spherical. That's the point of me drawing all that stuff together. Of course, this is done a little bit better with prettier balloons, right? So that's the reason why atoms are spherical. But it's not exactly a smooth transition. If you try to chart the charge of the electron density in there, it's not a smooth curve. And it's the same thing is true about an atom's nucleus. An atom's nucleus has really kind of funky density if you track it going through as well. So, okay, well, we're done with this chapter, and we're going to go on to the next one.